Hi folks, I'm just trying out a couple of different bits of software to try and record audio and video files so that we can use them for teaching and learning. I've been through Screencastify and Luma. They don't seem to work very well by my standards. So I'm using this one, OBS, which is open source and free. So it seems a bit more technical as well, which hopefully makes it better. Anyway, we haven't been able to start this year as we'd hoped, so we're not going to be able to do the Group 7 and the Group 2 tests. That those of you who hadn't finished it, we'll do that at a later date. Also CPAC 4, there was some things missing from there, ion tests and stuff. So again, hopefully we'll get a chance to get back in the lab and do that later on. For now, I want to continue on with the next topic, which is gaseous equilibrium, and that's all about the equilibrium constant Kp. You've come across Kc, which is for concentrations of solutions. Kp is for pressures of gases. So it's gas phase equilibrium, basically. And let's just quickly make a start on that. This should be enough to keep you busy for that first lesson next Tuesday. Let's look at what's underlined here: partial pressures, mole fractions, and the total pressure. Okay. Right, so partial pressures was a theory kind of thought up by a guy called John Dalton. That's a picture of him over there. And what he said basically is you sum up all the pressures of the different gases in a mixture and you're going to end up with the total. Okay, so it's pretty straightforward. You've got sigma pi individual gases, pressure of gas 1 plus pressure of gas 2 plus pressure of gas 3 gives us the total of all the gases combined together. So in this simple example down here, you've got oxygen at a pressure of 159, you've got nitrogen at 593, and if you combine them together in the same size container, you can't obviously change the volume, same size container, then you're going to have to just sum the pressures to get the total pressure, which in this case is 752. Okay, you might have come across these units before: millimeters of mercury, mmHg. They use it in geography to measure air pressures, and something called a YouTube manometer. Okay, so mole fractions. Now, you know that 1 mole of any gas, the molar gas volume, is 24 dm cubed at room temperature and pressure, 24 liters. That means that any gas, doesn't matter what it is, oxygen, nitrogen, hydrogen, sulfur hexafluoride, if it has the same number of particles as any other gas, then it's going to have the same pressure. Okay, it occupies the same volume and it'll have the same pressure if it's put in a similar container. Okay, so basically the pressure of any gas is proportional to the number of moles of that gas. Yeah, if you've got a container and you've got 1 mole in it and you double that to 2 moles, then the pressure is going to double as well. Yeah, so you know that sign from mathematics, directly proportional. Partial pressure, or even pressure, is directly proportional to the moles of the gas. Okay, so the moles of a gas as a fraction of the total moles in a mixture, we're talking about a mixture as well now, is what's known as the mole fraction. So looking at this little diagram here, you've got 2 diatomics, red one and the white one, and if we wanted to work out the mole fraction, and this is always going to be less than 1. 1 would be 100% if there was nothing else in there. It's always going to be less than 1, 0.8, 0.6, 0.5, 0.2, whatever. If you wanted to work out the fraction of that container that is the red ones, the red diatomics, then you'd take the number of moles of the red diatomics, you divide it by the sum of all of the number of moles of everything in there. Okay, in this case, red and white. And similarly, the partial pressure is equal to the mole fraction, that's that decimal like I was saying, 0.8, 0.6, 0.4, times the total. So let's say you had 50% moles, you got a number of moles in here, 50% of them were red and 50% of them were white, then the mole fraction would be 0.5, right? And whatever the total pressure was, then the partial pressure of both of those different diatomics would be half of that, 0.5 times the total pressure. Okay, so I've just written those down again, those two equations. They're pretty straightforward, you know, the three-piece equations, very easy. So I don't know if any of you dive. I know Josh does, Josh Lindsay. But do you know why it's quite dangerous for divers to fill their tanks with pure oxygen? The reason being is because the partial pressure of the oxygen that we breathe, yeah, let's say it's 1 atmosphere, is going to be about 20% of that, right? Which is zero point 0.2. Yeah, it's 0.2, the partial pressure of 1 atmosphere. And obviously the rest is going to be nitrogen, 0.8, and a little bit of some other stuff, but that's not so important. So if you fill a tank with pure oxygen, then it's no longer 0.2 times 1 atmosphere, it's going to be 1 times 1 atmosphere, which means, you know, you've just multiplied the pressure by 5. And obviously, if you go down deeper and deeper, then the pressure gets more and more. You know, that's how a regulator works. When you breathe the gas through it, it kind of maintains the pressure at the similar pressure of what the water is down there. And obviously, that's going to be toxic. Yeah, the more we increase the pressure of a gas, the more reactive it becomes. It becomes dangerously reactive, toxic in our bodies, the oxygen at high pressure. So very dangerous for divers to accidentally fill their tanks with oxygen rather than air. There are other mixtures, but anyway, we won't go into that now. Right, now I want you guys to have a look at this simulation. What you're going to have to do is go to my website. I shared the link with you last time. It's got all my resources and stuff. If not, I'll put it on Google Classroom again now. But please make sure you bookmark that for future. Go to this link, which is there, and I then want you to log in. You're going to have to log in to FET to actually access the document behind this link. Okay, and it's got instructions in it, and you've only got to do part 5. So you go scroll down to the bottom of the document once you've logged in, and then you should be able to do just part 5, which is about partial pressures. Okay, and after that I'd like you to do the multiple choice questions, and there's some other questions after that. Okay, so that should keep you busy for one whole period. Okay, right. Hopefully I've explained everything there. If there's anything you're not sure about, just put something in the comment section of Google Classroom. Okay, please do give me feedback on this audio visual media. You know, I hope it's coming through loud and clear, and it's quite clear visually and audibly. Okay, see you later.